Hello and welcome back for another little music production and Max for Live tutorial. Today we're going to have a look at phaser audio effects. We're going to find out how they are actually processing our input signal, what are the technical basics behind it, and of course we are building one for ourselves in Max for Live. So at first we're loading up an instance of the phaser flanger effect in Ableton Live and put it between two instances of the Berthel EQ curve analyzer. And as you can see, there is some notch filtering going on here. These notches are kind of moving around in the frequency spectrum because they are modulated by an LFO. If we turn up the notch parameter, you can see we basically just increase the number of notches. The speed of the modulation is controlled by the rate parameter. And we can, of course, phase offset the modulation part on the left and right channel for more stereo-like effects. The amount is basically the depth of our modulation range. So if we turn it up, the movement of the notches will be a little bit wider across the frequency spectrum. And last but not least, there is the spread value. And this is kind of the Q or resonance factor of our filters. And if we increase or decrease the value, our notches will be wider or more narrow. Now let's switch over to Max for Live and have a little look on the technical details there. The notch filtering in our phaser effect is created by blending a phase shifted signal with our original input signal. So to introduce some phase shifts, we are using all-pass filters. So we are creating some biquad objects and chain them together, like this. And now we're going to introduce our blending. So we create a plugin object and connect it to our filters. And then we add a plus operator to add our processed and our unprocessed signal. And to gain match both of these, we multiply them by 0.5. Now we have to declare the filter coefficients for our biquad objects. Of course, we are using the filter coefficient object for that and give it the attribute all-pass. Now we're connecting the inlets of the biquad object to the outlets of the filter coefficient object. And we're going to duplicate these patch cords and connect them to all of our biquad instances right here. Let's root them for a little bit better overview. And now, since we don't want all of our all-pass filters to be in the signal all the time, we're creating a selector object with the attribute 7 for each of our biquad filters. These can, of course, vary on how many notches you want to introduce. Connect them to our selector object. Also routing these patch cords. And connect the selector to the plus operator. Now we can start to declare our input parameters. So we create a signal operator and connect it to the selector. The +1 object I'm adding here right now is totally wrong, so you don't need that. Somehow the Max for Live device I exported actually worked anyway, although it shouldn't. I just saw that in the post-production process of this video and I don't want it to re-record all of that. So just, don't add the +1 operator right there. Sometimes Max is just doing weird things. And now we are creating a plugout object and connect it to the multiplicator operator last in the chain. And to make it a little bit more easy to watch, we are just encapsulating all of this with Command-Shift-E into a subpatcher and call it all-pass filters. So we have more space for further patching. Also, we're moving up our parameters a little bit right here. Of course, we want to process left and right channel independently, so we copy over the all pass filters right there and connect it also to our signal objects right there. And this should have been on the left side, and this is the right channel. Let's move those a little bit down so we can create our input objects. I use live dials for that. Under prototypes, there already is an amount dial, which we connect to the signal operator. And we give it the name order, or you could also name it notches or instances or whatever. And we give it the range 1 to 7. That is actually why we don't need this +1 operator right there, because our lowest input value already is a 1, so it's not 0 based. Now we're copying the live dial and choosing the Q prototype. And now let's choose the right parameter range. Maybe we get very narrow here, give it a 16 instead of a 10. And I think we call it spread, like in the Ableton one. All this parameter naming stuff, of course, is up to you. Do it however you want. Let's also give it an initial value of 0.7071, which is the square root of 0.5. And let's do another dial, set it to frequency. Let's give it a range from, I don't know, 50 to maybe 18,000, which is pretty high actually. And an initial value of, let's say, 500. And because we need a frequency dial later on for our LFO, let's call this center. Now we're actually done with our processing right here. But we only have a wet chain now, so we just gonna create a dry wet option. So we add a plus operator right here and add the processed with the unprocessed signal. And let's do the same for the other side. Then we just have to create some multiplier objects and connect them to each of these chains. Right wet channel and dry channel. And on the left, wet channel. And another one for the dry channel. So we're duplicating this for our dry wet input parameter. Let's move all this a little bit more close together. And I already made a prototype for dry wet mixing right here. Change the patch code over to the right outlet. And connect the signal operator to our wet chain. And then we need to reverse subtract from 1 to scale our dry chain. Let's bring that closer together a bit and route the patch cords. And move all of that a little bit down. Because now we actually need to build our LFO. To design LFOs, we typically using the phaser object. Let's give it a value input. Set the prototype to frequency. Give the range from 0.05 to 30 or something like that. We also should declare an initial value. Let's make it 1. The phaser object is giving us a RAM from 0 to 1, which can be remapped with other objects. Like the triangle object, we give it a range of 0.5, so it's actually a triangle with a centered peak. And the cycle object which is giving us a sine wave if we connect it to the right inlet, which is the phase. Then we add another selector object, so we can choose between both of these wave shapes. Copy the dial again. Now we need a +1 operator actually. And instead of a dial, we are using a live.tap object right here. And because the live.tap counts from 0, the +1 is actually needed there. Call it LFO shape. If you use 2 words, you have to set it in quotation. And give it the range triangle and sine. Initial value of 0. But we can do another cool thing here. We can use pictures. We can use the up-down SVG for the triangle and the sine.svg for the sine wave. And now we can see these little cool wave shapes right there to have it a little bit more visually appealing. Now we create a multiplicator because of how we want our frequency to be modulated right here. Another one for the other channel. And let's route these patch cords right here and move that over a little bit closer to the LFO. And now we're getting to our modulation range, which is a little bit more mathematical, but nothing too fancy. We just want our center frequency not to be scaled like in a linear way, because typically most phasers handle it like if the LFO is on its maximum, it's multiplied by a certain value, and if it's on the minimum, it's divided by the same value. So we need to add a POW operator right here. And this will raise the input value by the exponent of 16. This we connect to our multiplicator right there at the center frequency part. And because we want that to be scalable, we add another multiplicator object right there. And add another input parameter right here, which is the depth parameter. I also made a prototype for that. We also have to connect it to the right outlet again and connect it to the multiplier right there. And since we want to offset our LFO for the right channel independently, we have to copy all of this stuff once again. Then we create a plus operator to offset the phasor by a certain amount. Connect it to the phasor object, of course. And then we need a modulo operator with the attribute 1. So it will always put out the remainder of our phasor value plus our offset value. Of course, we also need to connect the selector to our live.tap chain right there. And now we're creating our last parameter, the LFO offset. Let's do this with the amount prototype. Change the patch cord to the right outlet. And we call it offset. The range and the initial value is fine this way, I think. And because we want the offset to be at its maximum, so at 180 degree, when the offset value is 100%, we have to multiply it by 0.5. Now we just connect our multiplier right there and this to the depth parameter. And now we should be good to go. And that's how you build your own phaser effect. As always, I exported a little Max for Live device from this patch, which you can find on my Patreon page. I also added some little comments in the patch there where each part of the processing chain is explained with a few words. And if you like the tutorial and want to support my work, you can of course become a Patreon member or check out my other Max for Live devices in my Gumroad shop and leave a little donation there if you like. And of course, you can subscribe to the YouTube channel so you don't miss out for further tutorials or plugin demos or whatever. And if you have any questions or feedback, you can just leave a comment or reach out to me via mail on my website or my social media. That's always very appreciated. And I hope to see you in the next tutorial.